So we just talked about the atomistic origin of elasticity, and now we want to kind of expand a little bit further. We just saw forces related to the derivative of our potential. The Young's modulus is related to the second derivative, so the stiffness, the curvature. And we have one more basically material property, critical material property, the thermal expansion coefficient, alpha, which is basically how much something expands meter over meter, the strain per inverse K. Those are going to be our units. And our thermal expansion coefficient is also related to our potential. So let's look at our Lennard-Jones potential again. So if I'm an atom here, and let's say my temperature increases so that I could kind of fluctuate, right? Back and forth, back and forth, back and forth. So if I move apart like this distance, basically you can kind of look at this distance here. I move this distance up my curve. If I move the same distance, this looks pretty, a little bit similar, maybe a little bit shorter. But you can see, let's just look at it like this. What's a lower energy? This state or this state right here? Clearly, because of the anharmonic shape, or basically the non-symmetrical shape of our potential, if my atoms get closer together, I move higher up my energy curve. That's bad. As my energy increases, I have more energy, more ability to kind of fluctuate and move, and the atoms can vibrate. But they want to vibrate such that the atoms get further apart, right? Because the energy penalty I pay for moving up here is much less. So for example, if I'm going to go like this whole distance here, if I'm going to go this whole distance here, which is pretty close, eyeballing it, this energy, excuse me, is much lower than this energy here. So even when you increase the thermal energy in your system, the lower energy state that your atoms are going to most likely exhibit is when, basically the atoms are further apart. Now this begs the question, what does the potential look like for a negative thermal expansion coefficient material? Well, it'll just be, the energy will be lower. Maybe, for example, maybe the well is very, weak and it's going here, whereas this one goes quickly up. There could be something you could imagine, something like that happening. But anyways, this is the origin of why materials will typically expand. And it's because, again, from that equilibrium distance, they are going to most likely be distributed at distances greater than the equilibrium distance. And because of the asymmetric or anharmonic shape, they're going to tend to basically deviate further and further apart because they adopt those lower energy positions. So 0K, we're going to be at R naught. Other than that, it is going to shift, and it's going to shift. This is our thermal strain. Very, very, very important equation. This only applies to normal strains. And basically, we will never exhibit it. Thermal strains do not occur for shear strains. Whether that be basically engineering or tensorial. So here are a couple of values. So for most linear isotropic materials, they'll expand uniformly in all three dimensions, so all three directions. No shear strain from thermal expansion, and these are typical values, again, multiplied by 10 to the minus 6 inverse K, and you can kind of prove to yourself that those have to be the units. But you see that polymers, they can expand. Again, thermal expansion coefficient is also kind of related to those interatomic bonding too, potential, so you can kind of see some of those values. You could also, as you cool or as you heat up material, you could actually induce residual stresses due to incompatible thermal strains. And we'll talk about that a little bit later. So, we mentioned briefly in the last video about sometimes the origin of elasticity can come from that basically entropic component. And so we're going to see that in action in just a bit. So thanks, and see you in the next video. Bye.